Okay, today we're going to be talking about another type of series, and it's called the alternating series. And this is the first series that we are going to discuss that actually has terms that are not all positive. Most of the series we've looked at, if not all of them, have been with positive terms. And now we're going to look at some series that actually include positive terms and negative terms. And so this is the test called the alternating series test. This should be the 7th test in a group of 10 tests that you will learn to prove whether a series actually converges or diverges. And this is a very simple test. Basically, it says that if you have a series, and we'll call this series the summation from n equals 1 to infinity, you have -1 to the n, or some function that makes the series alternate in terms, and a sub n is just the piece that is next to the alternating part. That series is going to converge if two things are true. First, if n approaches infinity, if a sub n equals 0, and a of n plus 1 is less than or equal to a of n for all n, which actually is technically not correct. We're going to say that it eventually decreases. Eventually it decreases. It may not decrease immediately, but after it starts decreasing, it continues to decrease. So let's break this down and make it very simple. An alternating series converges if, first, you can show that the terms are alternating in their sign, plus minus, plus minus. Second, you have to show that it is decreasing in its magnitude, meaning the absolute value of the terms, and it has a limit of 0. So let's see if we can jump in. First one, letter A. Is this an alternating series? Well, you have to pay attention to this portion of the series because sometimes they will try to trick you and they may put something like this, -1 to the 2n, where you may think, oh, it's -1 to a power, that automatically makes it alternate, but notice 2 to the n guarantees that it will always be some sort of even number. So -1 to any even number will always be a positive 1, so that actually does not cause a alternating situation. However, in our case, that's not what we have, but I wanted to make sure that you were aware of that. So we will erase that. And so we see that this is first and foremost alternating in its sign. So has alternating terms. So you'll check that off. Second thing you have to prove is that this is a decreasing function. So we will take n over 2n minus 1. And actually, you know what? We're going to do the limit first instead of that. So let's just take the limit as n approaches infinity of this piece. And notice what we get. We get 1/2. 1/2 is not equal to 0. And in order to use the alternating series test, you have to get a limit that's equal to 0 to show that it converges. Notice we got a limit that's equal to 1/2. So this series diverges. However, it does not diverge by the alternating series test. The alternating series test only proves convergence. So let me write that down. Only proves convergence. This series diverges because of another test. It diverges by the nth term test. It diverges. So be careful of that, all right? So you don't need to go any further. You don't need to show that it is decreasing. So let's move on to the next example. Cosine of n pi over n to the 3/4. Now, at first glance, this does not appear to be an alternating series. However, if you plug in various values of n, let's say we'll start with 1. So you have cosine of 1 pi. That's going to be -1. And then you have cosine of 2 pi. That's going to be 1. And then you have cosine of 3 pi. That's going to be negative 1, and you can see the pattern. It goes from negative 1 to 1, negative 1. So this really, if you wanted, you could rewrite this as negative 1 to the n over n to the 3/4, since cosine of n pi is equal to negative 1 to the n power. All right, so we have proven, first of all, that the terms are alternating. So alternating terms, check. Second thing you have to prove is that it is decreasing in its magnitude. So for this, a simple plugging in of terms, or you could just look at the graph and you can see that this graph, let's say when n is 1, you have that right there. And so this graph is looking like that. And so it's going to be a decreasing graph. If you want, you could actually use the derivative test, and you could show that the derivative is always negative. So why don't we do that really quickly? Let's say we have f of x equals 1 over n to the 3/4. So I'm going to make that n to the negative 3/4. And so f prime of x is equal to negative 3/4, and this should be an x, so we'll change that, x to the negative 7/4. So you can see that f prime of x is always going to be negative, which means the function is decreasing. So you have to find a way to show that the function is decreasing. So the third thing you have to show is that the limit goes to 0. So the limit of 1 over n to the 3/4 as n approaches infinity is simply going to be 0. So we have proven all three of these. That means that this function converges by the alternating series test. And that's all there is to the alternating series test. Okay, the next thing we're going to talk about is something called the alternating series remainder. And this can be a little bit confusing, so I'm going to try to take it slow and explain this. If you have a series that has these three conditions, first, the terms are alternating, second, decreasing in magnitude, and third, the limit is 0, then the series converges. We've already talked about that. That is the alternating series test. Now the question is, can we find what it converges to? Now remember, there are only certain series that you can determine what the actual sum is that the series converges to. Geometric series is one. Here's another one, the alternating series. We can get an idea, or at least an approximation of what the sum is, S. And it says if the sum S is approximated by the nth partial sum, and we'll call that S of n, then the error in the approximation, R sub n, which equals S minus S sub n, will be less than the absolute value of the first omitted or truncated term. And you're thinking now, what in the world does that mean? Okay, let's see if we can explain it. In English, it means if the series is convergent, okay, that takes care of those three conditions, you can approximate the sum of the series by adding up the first n terms, and the sum of those n terms, which we are going to call S sub n, will be correct within the value of the first neglected term. So let's just see if we can break this down. Let's say we have some function, or should I say some series that gives us the following terms. 1, and then minus 1/2, and then plus 1/3, and then minus 1/4, and then plus 1/5, and then minus 1/6, and on and on and on. Okay? What this is basically saying is that I can approximate, well, first of all, the real sum, S represents the sum of all terms. That's what S represents. An infinite number of terms. S sub n represents the sum of a certain number, n, of terms. That's why it's called a partial sum. Now, R is the difference between the real sum of all a million gazillion terms and the number of terms you decided to actually add together. That difference between the actual, so why don't we say this? This is the actual, and this is the, we'll put quotes around that, this is the approximated sum. Didn't spell that too well, but you got the idea. The difference between the actual and the approximated is called the error. It is it's the error that you are assuming when you find this approximation. All right, so that is your error. And what this is basically saying here, this remainder is saying that the error that you get is going to be evaluated by the value of the first neglected term. So let's see if we can make sense of this. Let's say we want to approximate the sum of this series. So let's say we want to add up the first three terms. So this is my first neglected term. So let's just add up the first three terms. You have 1 and negative 1/2. That is 1/2 plus 1/3. So 3/6 plus 2/6 is 5/6. 5/6 represents the sum of the first three terms. Now, the first neglected term is 0.25, and we're taking the absolute value, 0.25. So what this means is this sum, 5/6, is correct within plus or minus 0.25 either way. So we'll come over here and we'll say the real sum, S, is equal to our approximation, which is 5/6, plus or minus 0.25, or 1/4. So if you add 1/4 to 5/6, or if you subtract 1/4 from 5/6, the real sum is going to be guaranteed to be somewhere in that window. So maybe we'll work that out. 5/6 plus 1/4 is, let's see, this is 10/12 plus 3/12, and that's 13/12. So the upper bound is 13/12. So upper bound is 13/12. And now we're going to subtract it. So it'll be 5, we'll say 10/12 minus 3/12 is 7/12. So that's our lower bound. Our lower bound is 7/12. So what this is saying is, if I can find some space, the real sum is going to be guaranteed to be somewhere between 7/12 and 13/12. And that's basically the idea behind the alternating series remainder. Okay, this next example says, given the series summation from n equals 1 to infinity of -1 to the n plus 1 over n factorial, approximate the sum S of the series by using its first four terms. So, first thing we need to prove is that this is a convergent series before we even use anything else. So, we see, first of all, that it is an alternating series. So, it's alternating in its terms. Check. We see that the limit as n approaches infinity of, strip away the alternating part and just analyze 1 over n factorial. That's clearly 0. And then the third thing we can see is that it's decreasing in its magnitude, and that's pretty obvious. You have n factorial on the bottom. The bigger n gets, the bigger the bottom gets, which means the overall number is getting smaller and smaller, so it's decreasing. So we're going to approximate this sum using the first four terms. So we're going to plug in n equals 1. And when we plug in n equals 1, we get -1 squared, which is 1, over 1 factorial, so 1 over 1. And then n equals 2 is going to give us 2 plus 1, that's 3. That's negative 1 to an odd power. So that's going to be negative 1 over 2 factorial, which is 2. And then it's going to alternate to 1 over 3 factorial. And once again, let's remember factorial is 3 times 2 times 1. So that's going to be 6. And then the next one is going to be minus 1 over 4 factorial, which is 24. And then 1 over 5 factorial, which is 1 over 120. All right, so now it says approximate the sum of the series by using the first 4 terms. So that's going to be these 4 terms right here. This is our first neglected term. That's going to come in handy in just a moment. So if we add up the first 4 terms, we get 0.625. So that is an approximation. So let's write this down. That is an approximation of the real sum S. And that's what we have. We're using just the first 4 terms. Okay, part B says explain why the estimate that we found in part A, and let's remind ourselves what that is. We found that the sum of the first 4 terms, call that S4, was 0.625. And it says explain why that estimate differs from the actual value by less than 1 over 100. Well, if you can remember, the first neglected term was 1 over 120. And so if you divide 1 over 120, that is 0.0083. And so what we'll say here is that the actual sum minus the approximated sum, so let's write that out, actual minus approximated, is going to be less than or equal to 0.0083, which is clearly less than 1 over 100, which is just 0.01. So the first neglected term, once again, tells you your error. And so we prove here that it differs from the actual by less than or within 0.01. Okay, part C says use your results to explain why the actual sum S could never be 7. And I believe that probably should say 0.7, but it doesn't really matter. Use your results to explain why the sum could never be 0.7. Well, we found that our first 4 terms were 0.625. We found that our first neglected term was 1 over 120, which is 0.0083. So if we take our approximation and we add to it 0.0083, we will get an upper bound for our sum. And if we take our 0.625, our approximation, and we subtract the value of the first neglected term, we will get a lower bound for our sum, approximation. And so if you work those out, basically what you have is 0.616, and this is repeating, is less than or equal to the actual sum, which is less than 0.63 repeating. So the real sum has got to be bounded between here and here. So obviously the more terms you add together, the more precise you will get for your approximation. Okay, example 3. How many terms are needed to approximate the sum of the series summation from n equals 1 to infinity of negative 1 to the n plus 1 over n to the 4th, so that the estimate So the estimate or approximation differs from the actual sum by less than 1 over 1,000. So basically, we want to find the first neglected term that is smaller than 1 over 1,000. So let's write out some terms. When n is 1, you have 1 over 1. When n is 2, you have negative 1 over 16. When n is 3, you have a positive 1 again over 3 to the 4th, which is 81. And then a minus 1 over 256. And then a positive 1 over 1296. So let's just write out some decimal equivalents here. So we have 1. And then, so maybe we'll do this in a different color. So the decimal equivalents are, this is 1. And then 1 over 16 is 0.0625. And then 1 over 81 is 0.0123. And then 1 over 256 is 0.0039. And I forgot a term somewhere in here. And that term should be 1 over 625. And that makes this term a negative. So excuse me. It should be plus 1 over 625 and then minus 1 over 1296. So 1 over 625 is going to give us a decimal value of 0.0016. And then 1296 is going to give us 0.00077. And so if you notice that this term, 1 over 1296, is the first term that is less than 1 over 1,000. Well, let's just review. 1 over 1,000 is 0.001. And so this is the first term that is actually less than 0.001. So the approximation is going to be plus or minus 0.00077 if we use 1, 2, 3, 4, 5 terms. So the answer to this would be it takes 5 terms to get an approximation that is within 1 over 1,000 of the actual sum. All right, in this last example, it says approximate the sum of this series correct to 4 decimal places. So let's just start writing out some terms, and we're going to assume that this is a convergent alternating series. So when n is 1, and you will need your calculator for this, unless you feel like doing a lot of heavy math. When n is 1, you have negative 1 to the first, which is negative 1 times 1 over 8. So that's going to be negative 1/8. And so when n is 2, you get 2 over 64 positive. When n is 3, you get minus 3 over 512. When n is 4, you get a positive 4 over 4,096. When n is 5, you have a negative 5 over 32,768. And when n is 6, you get 6 over 262,144. Now, once you start getting to a term that you think may be correct, just use your calculator and divide it. And you notice here that 5 over 32,768 is 0.00015. Well, if you notice, that only has 3 decimal places of accuracy. So we need to go one more step further. So 6 over 262,144 gives you 0.0000229. And so that gives us 4 places of accuracy. And so that means we neglect the sixth term, and so we are going to use the first 5 terms to approximate the sum. So our answer is going to be S of 5, which is the partial sum of the first 5 terms, is going to be negative 0.0987. And that's the approximation of the actual sum plus or minus 0.0000229 in either direction.